this is Aaron Crimmins. I'm the creator of the MindMaker Machine Learning Plugin for Unreal Engine. Today we're looking at how MindMaker can be used to enable self-piloting boats within a game simulator. Let's begin with an overview of the motivation for this project. While some of us may find it fun to watch virtual boats crashing into virtual walls for hours on end, there are actually real-world consequences being explored through this project. The idea behind the setup is that by teaching boats to navigate autonomously via reinforcement learning algorithms within a game simulator, we can later transfer those trained algorithms to real-world boats so that they can navigate just as a human would. One of the main advantages of training self-piloting boats within the simulator is that when mistakes are made and the boat crashes, there are no real-world consequences. And we can debug these algorithms within the simulator without risking anyone's life. These techniques don't merely apply to boats. As the gap between our simulators and the real world continues to narrow, tools like MindMaker will allow us to develop autonomous navigation for a variety of mobile platforms. Everything from boats and cars to bipedal robots. So to summarize, we train our algorithms in the simulator, and if we have our physics and other environment variables set correctly, then those algorithms can be exported to real-world environments and perform similarly. Let's talk for a moment about the simulator we are using, Unreal Engine, because that's an important piece of the puzzle. For those unfamiliar with Unreal Engine, I'll give a quick overview of why it's useful in autonomous navigation tasks. Unreal Engine started as a tool for building video games, but it has since evolved to become much more and is used in everything from 3D architecture to movie production. Unreal Engine represents the absolute cutting edge in photorealistic 3D scene creation, to the point where one can sometimes find it difficult to distinguish between actual video footage and virtual worlds created in Unreal Engine. And unlike other 3D content creation tools, Unreal Engine combines the same visual components that one might find in Blender or Autodesk Maya with a real-time physics engine and a programming interface for manipulating the content on the screen. Thus, it provides a kind of all-in-one desktop environment for manipulating virtual worlds and creating ones that mimic our own in really important ways. So this allows us to experiment with autonomous navigation without actually damaging anything and using the same physics and environment variables that are important in the real world. And then we can transfer those trained machine learning algorithms back into the real world once they're fully optimized. So to understand how this can be done, let's start with a high-level overview of the machine learning that is being used in this autonomous navigation task. So one of the ways to approach autonomous navigation is to gamify it. That is, we create a scenario in which our AI gets rewarded if it successfully learns to steer around objects and avoid collisions. How can we go about doing that? Thanks to a really fairly new kind of AI called reinforcement learning, we can use trial and error methods to reward the AI if it takes an action that avoids a collision and punish it if it does collide. So without getting too deep into the math of reinforcement learning, essentially we let the AI experiment over thousands or millions of training episodes until it gradually can recognize when it took an action that led to it avoiding a crash and when it took an action that led to a collision. So at first the AI makes a lot of random decisions or movements, and when those movements result in a collision, it gets punished, and if it results in a reward, that reward modifies a neural network, the weights and biases of the neural network, so that the next time the AI is in a similar situation, the neural network recognizes those components of the environment, and it will be more likely to take the action that was rewarded than the one that was not. So in this way, it's a lot like training a dog, or even how we humans learn to walk. When we are infants and first learning to walk, we use something called motor babbling. We essentially make random muscle movements. And when some of those help us move forward or crawl, those actions get rewarded by our dopamine system, and we begin to repeat them more often. So reinforcement learning actually has its origins in animal behavior and was discovered by scientists attempting to model how animals learn from rewards and punishments. So there are really three basic components to the reinforcement learning schema. There's the action, there's the observation, and there's a reward. And there's the environment. I guess that's the fourth thing. So the agent takes an action in an environment that produces two things, rewards and observations. And those rewards and observations get fed back to the algorithm, and then it modifies its actions based on those rewards and observations. So now that we have a kind of high-level understanding of reinforcement learning, let's walk through how it's being implemented in this particular case. So the MindMaker plugin that I developed enables a kind of universal framework for transforming any Unreal Engine environment into a format which we can apply Python-based reinforcement learning algorithms, including those that work with TensorFlow and PyTorch. For those that are familiar with that, those are TensorFlow and PyTorch are some of the neural network math libraries in existence today. And the universal reinforcement learning framework that MindMaker uses is known as OpenAI Gym. And that was developed to standardize all of the components used in reinforcement learning. And this means that we can test a large number of RL algorithms on a single environment quickly and benchmark them against each other. So in our case, we're applying the Stable-Baselines suite of reinforcement learning algorithms, which includes many of the famous ones like those used to defeat best-in-class Go players. Perhaps some of you may be familiar with AlphaGo. That was a Google-trained reinforcement learning algorithm that defeated the world's premier Go player. As a side note, RL algorithms currently hold the record for the best chess AI at the moment. And these are very powerful and very versatile algorithms. And MindMaker really contains a lot of the good ones like proximal policy optimization, actor critic, deep Q learning, and more. So now let's walk through the Unreal Engine blueprint implementation. And we're going to switch gears here and move over to Unreal Engine blueprints. And there are really two significant components to MindMaker. One is a blueprints plugin, which you kind of see on the screen here. And the other is the actual RL algorithm, which is, you can't see because that's located, well, we can actually bring it up here. This is a separate executable that contains the RL algorithm. And you saw it just being trained there. So what's flashing on the screen here are actually observations and rewards and actions. So that's all that the algorithm needs. It doesn't need everything that's happening in Blueprints or Unreal Engine. So these two components, the algorithm and the Blueprints plugin, communicate via a socket.io client connection, which is right up here on the left-hand corner of the screen. So we need to add that to our Unreal Engine game component in order to make it into a MindMaker actor. Let's actually dive into some of the MindMaker settings here. the launch MindMaker function is really the heart of the action. And that's where we can see a lot of the important settings. So we have right here the RL algorithm that we're training with. In this case, it's A2C, actor critic. And the next important one we're going to talk about, let's talk about the observation space shape. Because this is really where we define the environment that the algorithm is learning from. And as you can see, it's just an array of 4 or 5 values with the lows defined and the high values, array of floats. So most of what we saw on the screen here is actually just window dressing. And what we really care about, or what the algorithm cares about, is the ray traces. So let's go back to that real quick. See these red laser-like things shooting out of the boat are measuring the distance between the boat and the walls or any other objects that it's facing. So that is going to be our observation space, those 5 different ray traces. And we define those here, their values. So the next thing we need is an action space. And that is going to be how the algorithm actually makes adjustments to the boat. And in this case, it's the values that the rudder can take to steer it right or left. So left being -2, right being +2. And this is the all those intervals between that being variations of how the rudder can move. So at the point that we would actually transfer this into the real world, we would replace the observations with like LiDAR or radar readings that would be updated in real time. So there's a variety of other MindMaker, besides the action space and the observation space, we can see there's a variety of other settings in the MindMaker launch MindMaker function. I won't go into all of them in too much detail. Saving and loading your trained model. Important ones are the custom parameters. So we're going to drill down into the A2C custom parameters. These are also known as hyperparameters, and they can control all of the different ways we can fine-tune one of these algorithms, including the depth of the neural network being used, the learning rate, lots of different ways we can tweak things. So now let's walk through a single training episode so we can see how all of the elements we discussed in reinforcement learning overview come together to create an actual training episode. So we discussed the action, the observation, and reward. So we're going to begin with an action, and that's actually, as soon as this simulator gets launched, the separate MindMaker executable starts creating actions over which that space we defined it. So -2 to +2. So it communicates an action to Unreal Engine, to Blueprints, which is received in this function over here on the left, receive action. And that action, basically, it comes in as a JSON format, and we update the Blueprints variable action selected to be the new action, and our boat's rudder immediately gets updated in real time based on that action that was produced by the algorithm. So once the action has been modified, the environment, it will produce a set of observations. So we go to the display, and those observations get recorded here in make observations. So there's action taken. Now that results in a set of observations, which are these traces, these 5 line traces. Next, there's a reward. We want to check if the boat hit something or what's the distance to the walls. So we have our array of traces, and we want to get the minimum, how close it is to a wall. We also want to know if the boat hit something. If it did, we set a reward, a big negative reward here. Once we now have made observations, we've checked for a reward, then we want to pass this back to the learning algorithm, executable. We do that through this set members in MindMaker custom structure. We collect the observation and reward, and we emit it through a socket IO connection. And we encode it in JSON, and we send it basically like over the internet to wherever our MindMaker client is located. Well, this is the client. Wherever the server is located that has the MindMaker executable. In this case, it's on the same machine, but you could actually have them remotely, and there would be many good reasons to have the MindMaker algorithm remote, because you could have it on a much more powerful machine than your client. And that's where you often need a lot of processing power, especially if we were learning from all of the pixels on this screen rather than just these 4 points, 5 points. We would want a computer with a very good GPU for processing all that. So we've now kind of seen how all of those elements come together and into a single training episode. And we actually will let it train for days, for thousands of training episodes. I mean, you can train these for weeks, and sometimes it takes that long to start getting good results. It's a very laborious, time-intensive process, but once you have it trained, you can use that trained algorithm, and it's already, it can recognize the walls, it will be able to avoid collisions. You don't need to keep training it, and you can save it and export it to other different boats. I mean, in this case, we're potentially exporting it to a real boat. So over time, over many crashes to the boat in the simulator, the algorithm gradually improves. So you can see that it's often making really dumb choices right now, and that's to be expected because it could take over 24 hours. But overall, you can see this is performing a lot better than chance. So something is happening, and it's gradually beginning to learn. And this is really, I hope I've communicated the magic of reinforcement learning, this intervention-based system that can actually detect cause and effect relationships. The cause being the agent's actions, and the effects being any rewards or observations that result from those actions. And without getting too much into the philosophy of how important reinforcement learning is, we can think of all of human science as the accumulation of cause and effect relationships in the form of our long-term cultural memory, be it stories, books, or other media. We pass on knowledge of these cause and effect relationships, and this allows us to improve our own decision making over time. So I hope you've enjoyed this video and found it informative. If you have further questions about MindMaker, feel free to reach out to me via email. I've put that in the video description.